Okay, so this is our circuit for the common emitter amplifier. So I'm setting up this circuit right here. I know we were struggling with the circuit a little bit, so I went ahead and made a video. Right now is Monday, you guys have class Thursday. This week, just trying to set this whole circuit up. So we have a 10 microfarad capacitor, okay? So you're looking for this black electrolytic capacitor in your kit, okay? 12 kilo ohm resistor, 1 kilo ohm resistor, 10 kilo ohm resistor, 100 kilo ohm resistor, okay? Be sure and note, do you have a pen?
No.
Okay, that's fine. Be sure and note, right, that this is the base side. The side with the arrow is the emitter, okay? And the side without the arrow, okay, that has the voltage output node, that's going to be the collector side, okay? So match this in accordance with the symbols that you see on the BJT themselves, right? The emitter is closest to the notch, right? On the right-hand side, collector is on the opposite side, base is in the middle, okay? So my circuit is set up in accordance with that, okay? Right, so my emitter is, if I go back to this circuit, my emitter is connected to 1 kilo ohm, okay, and that's going directly to ground, okay? So this yellow wire right here specifies where ground is, okay? And then I have my 12 kilo ohm resistor connected to my base, right? So I've created sort of a central node right here by using this white wire that you can see on your left, okay? Yes. So I have my 12 kilo ohm resistor going to ground. That's this resistor right here, okay? And then I have a 100 kilo ohm resistor that's going to my 10 volt DC supply, okay? And then finally, I have my collector, okay? That's connected to 10 kilo ohms, okay? So let's locate that. I have my large white wire in the middle right here, okay? That's going to designate my node in which both the 10 kilo ohm resistor and my voltage output are going to be connected to, okay? And then you can see, excuse me, that 10 kilo ohm is connected to 10 volt DC, okay? Okay, and then finally, the capacitor is connected to that central node. That's that white wire that you can see here on your left, okay? And then this capacitor is going to be connected to my 50 millivolt peak-to-peak. Peak-to-peak just meaning, okay, so if it's the amplitude, then it would be twice the amplitude, right? It will work on regular 50 millivolts amplitude, which would be 100 millivolts peak-to-peak, right? Okay, and then I'm setting my frequency at 100 hertz, okay? So I'm gonna turn everything on. Let's vary the voltage and let's vary the frequency and see how that changes the circuit, right? Okay, so let's turn this on. This is my DC power supply. You only have one output here, right? Okay, so you have 10 volts right here. And then immediately, without turning on output on my AC signal generator, okay, I should see some sort of change on my oscilloscope here, okay? So once again, this oscilloscope is connected to a T-junction for my AC signal generator, as well as my circuit itself, where the output voltage is on the collector side, right? Where's the other side of the node? The other side of the node automatically goes to ground, right? So whenever we write a node like this, we're assuming that if you were to write the plus and minus sign for the voltages, that the plus goes where the node is, okay? All right, so let's turn this off and let's see what happens to the oscilloscope, right? So you see some rise in voltage. I turn this off, that voltage falls. Yellow right here is my output signal, okay? I turn this on without any AC signal being generated, and then I see a slight rise in the voltage itself. Forget what's happening with the blue there. Blue isn't measuring anything right now. Okay, now I'm gonna turn on my AC signal generator, okay? So I'm pressing on the output here. I'm on 100 hertz, okay? 50 millivolts. I turn this on, let's see what happens, okay? So examine the output here, okay? Blue is my input, yellow is my output. Remember, in any sort of setting, okay, we have an active device, right? but our output is never going to be greater than our input in magnitude. Okay, so notice our blue here is much larger than the yellow. Okay, I've said don't trust the oscilloscope's illustration in and of itself. I've measured it already. Obviously, we should see that the blue signal's magnitude is much greater than the yellow here. Okay, but let's see what's happening, right? This is an amplifier. It should be amplifying the signal. Okay, so I have an input signal and I have an output signal. Okay, by varying the let's see, base emitter voltage. So that's the voltage on this side of the capacitor. Okay, so obviously this voltage right here, that's my AC signal, is going to vary the voltage from the from the base to the emitter junction. Okay, so by varying this voltage, I'm essentially doing something in accordance with this graph that I drew for you last week. Okay, so the idea is this: if the transistor is operating within its operating regime, okay, that signal should vary anywhere. So this is VCE right here, collector emitter, should vary anywhere between the cutoff region, right, where this is 0, to the saturation region. Remember, if you go beyond the saturation region, that transistor will completely, not necessarily cut off, but the output signal is then going to be DC, right? And then if you go to the cutoff region, then the output signal is also going to be DC as well, okay? So the goal here is to take some sort of inputted sinusoidal signal, output a sinusoidal signal that might be either attenuated or amplified, okay? So if I'm within the operating regime, then I should expect that amplifier to go anywhere between this large voltage or this small voltage right here, okay? If you see any sort of DC output on your supply, despite having an AC input, what does that mean? That means you're going beyond the operating regime, okay? If you're going beyond the operating regime, so let's say for instance, I go too high on my input voltage, okay? I go into the saturation region, what's gonna happen to my signal? My signal is going to look like DC, at least for a small part of the cycle, okay? And then I go beyond the cutoff region, the signal goes too low, right? Then it's also going to be cut off, okay? What's this region right here? We call that leg room, okay? So if the amplifier is not getting a perfectly sinusoidal output, okay, that means there's not enough leg room, okay? In other words, the base emitter voltage, that's the sinusoidal voltage, is not high enough, okay? And then if you're getting a DC, when the voltage is too high, then there's not enough headroom in that operating regime, okay? So let's see what's happening. So right now I am getting a sinusoidal output right here, okay? So it is working, okay? This is an amplifier. It will either attenuate, so it might make the signal smaller, or it will amplify. It might make the signal much larger, okay? So let's see what happens if we vary the base emitter voltage, okay? Remember, let's go back to our circuit, right? This sinusoid is connected to a capacitor, okay? What is a capacitor? It's an element that's dependent on frequency. Remember, the higher the frequency, the more this thing wants to act like a short, okay? For a long time, for steady state DC signal, this will eventually become, a short or some sort of simple DC model, okay? But in any case, if I vary the frequency, that's going to affect this capacitor. If I can change this capacitor to a short, or it can become a, or it can become an open circuit, right? Okay, so that's where the frequency gets involved here. There's also what we call oxide capacitance between the base and the either the collector and the emitter. Okay, so this amplifier itself is also, this transistor itself is also dependent on frequency. Okay, so let's vary the frequency first and see what happens. Okay, so I'm gonna hit frequency F1 function. Okay, and let's watch this. Okay, so I'm going to increase the frequency right now. Okay, so my input signal, that's blue, right? There's more cycles in some amount of time as I keep increasing this thing. Okay, now I've doubled the frequency. Okay, and we see that's happening on the output as well. Okay, the output's getting slightly smaller and smaller and smaller. Let's hit the auto scale function. Okay. Okay, now I decrease my frequency. Let's see what happens. Okay. So less cycles in some allotted amount of time. Okay, let's speed this up. All right, and then not very much signal that's getting parsed here, right? Okay, that capacitor is acting a bit like an open circuit in the low frequency regime. So it's not passing on that signal very well to the base. Okay, so now let me set this back to 100 Hertz. Okay, so let me put this very quickly. Okay, good enough, 100 Hertz. All right, now this is the last thing I'll say. I'm going to vary the amplitude. Okay, what does this vary? This varies the base emitter voltage. Okay, so let's say I have a very low, base emitter voltage, right? So let's hit the auto scale function. Let's see what's happening to my output. Let's see. Okay, so right now we're in the cutoff region. Okay, so the signal is being completely cut off. Okay, so I shouldn't see any signal on my output, okay? Or if there is any signal on my output, it's going to be a DC output, okay? Because we have gone beyond any sort of leg room for the operating regime. Okay, so now let's increase this voltage. Increasing this voltage, let's say, okay, let's go back to 50 millivolts. Okay, now I have a good sinusoidal output, right? Okay, now let's keep increasing just like we had before. Now let's keep increasing this thing, okay? So now I'm at 500 millivolts or 0.5 volts, okay? And do you see what's happening? What's happening with my output here in yellow? For a certain part of the cycle, it's becoming a DC signal. Why? Because it's getting cut off. That means I'm going beyond the headroom of the transistor itself, okay? So once you guys build this circuit, what I want you to do is vary the frequency, vary the base emitter voltage, okay? We can also vary the collector emitter voltage and see what happens as well, okay? And that's going to cause the overall signal to decrease, okay? So this signal is proportional to the essentially the voltage that I'm using to power this transistor itself. Okay, your output is going to be dependent on both your base emitter and your collector emitter voltage. So you notice here I have reduced this DC supply, okay, and then my output signal is going to heavily decrease as well. Okay, when I go down to 0, this whole transistor is now in the cutoff region. Okay, so now it's perfectly DC 0 volts. And now I increase this thing, and now you see a bit more of a sinusoidal voltage. Okay? All right, so once again, vary frequency, vary base emitter, vary collector emitter, and then you should see some interesting behavior, and hopefully you get a general idea of what's going on with these amplifier setups. Okay, thank you.